Welcome back to Math320 videos. In this lecture, we will discuss some issues surrounding doing arithmetic with Limsup and LIminf. These correspond to material on pages 78 and 79 of your textbook. The section of your textbook has some additional material in it. We will skip them in the video lectures since those material are mainly applied for studying the root test for convergence of infinite series, which we will skip in this course. Those of you who are interested in how the root test works should certainly take a few minutes to read the material presented in the textbook. Okay, let's get started. One of the things you may remember well from your calculus classes is that limits play well with arithmetic. We went through some of these in the previous few weeks. Let me capture two of the very nice properties of convergent sequences here. If x sub n and y sub n are two convergent sequences, then we know that the sequence formed by the products of xn and yn is also a convergent sequence, and that the limit of this product sequence is exactly the product of the limits of xn and yn respectively. Similarly, the sequence formed by the sums of xn and yn is also a convergent sequence, and that the limit of the sum sequence is exactly the sum of the limits of xn and yn respectively. Things get very complicated if we start talking about divergent sequences. First, it is very possible for sums and products of divergent sequences to be convergent. For example, if we set xn to be minus 1 to the power n and yn to be its negative, then the sequence of their sums work out to be the sequence of all zeros. And the sequence of their products work out to be the sequence of all negative ones. So we see that while neither xn nor yn converge, their product and sum do. Furthermore, we also see that products of a divergent sequence and a convergent sequence depends a lot on the details of how the divergent sequence diverges and how the convergent sequence converges. In the examples shown, xn always represent the divergent sequence and yn the convergent one. In the first case, xn equals n diverges and yn equals 1 over n converges. Their product is the sequence of all ones and hence converges. In the second case, xn equals n again, but yn equals sine n over n, which still converges. But this time, their product is sequence sine of n, which does not converge, though we stay bounded. In the third case, xn equals n squared and yn equals 1 over n, like the first example. But this time, the product sequence is set to n, which is unbounded and diverges. So what can we say about Limsup and LIminf when they are different? Remember, if Limsup and LIminf are different, the sequence diverges. Before getting to the answer, we introduce a preliminary lemma that will be useful in the discussions to follow. This lemma says that every number bigger than the Limsup is an eventual upper bound, and every number less than the LIminf is an eventual lower bound. Notice that this lemma is not automatic. Given an arbitrary set S, it is not the case that every number less than the sup of S is an element of S. It is also not the case that every number greater than the inf of S is an element of S. What we can say in general is that if a number is less than the sup of the set S, then there is an element of S that is greater than the given number. Here, in the case of the eventual upper bounds and eventual lower bounds, it turns out that it is the case, in contrast to the general setting, that any number greater than the inf of all eventual upper bounds is itself an eventual upper bound. And this has to do with how the set of all eventual upper bounds are defined. The proof of this lemma is not too difficult. We give the Limsup case here. The LIminf you should try to do yourself as an exercise to make sure you understand how the argument proceeds. We start by using the definition of Limsup as the inf over all eventual upper bounds. And since u is bigger than limsup, this means that there is an element u prime less than u that is an eventual upper bound. This is due to the definition of the infimum. But this means that for capital N, all further terms of x sub n are no more than u prime. But as u prime is less than u, this means that u is also bigger than all further terms of x sub n beyond capital N. But this is precisely the definition of an eventual upper bound. So we see that every number greater than the limsup is an eventual upper bound. The limsup itself, however, as we saw a couple weeks ago, may turn out not to be itself an eventual upper bound. A useful corollary of the lemma is that whenever u is not an eventual upper bound of the sequence, then limsup of x sub n has to be at least u. And similarly for the property of not being an eventual lower bound. This corollary is the direct contrapositive of the lemma above. The lemma says that if u is bigger than limsup, then u is an eventual upper bound. So this corollary says that if u is not an eventual upper bound, then u is no bigger than the limsup. Now we are ready to state the first theorem about arithmetic of limsups and LIMINFs. If x and y are bounded sequences, so in particular their limsups and LIMINFs exist, and assuming that x and y have positive terms, meaning that no term can be 0 or less, then we have that the limsup of the product is no bigger than the product of the limsups. Again, the limsup of the product is no bigger than the product of the limsups. Let's discuss how this can be proven. What we will do is to prove that every number that is bigger than the product of the limsups must be an eventual upper bound of the product sequence. If so, since the limsup of the product sequence is the infimum of all of its eventual upper bounds, and that the set of all numbers bigger than the product of the limsups is a subset of this set, we conclude that the limsup of the product sequence can be no bigger than the product of the limsups. The logic of this step is a little bit involved. You may wish to pause the video to think this second step through. In order to establish that every number bigger than the product of limsups is an upper bound for the product sequence, we will treat separately the case where at least one of the two limsups is 0, and separately the case where both of the limsups are non-zero. We start with some prep work. Notice that since the terms of the two sequences have positive terms, this means that 0 is not an eventual upper bound. And therefore, from our corollary before, the limsup of the two sequences are both at least 0. We let u and v be two numbers bigger than the two limsups, and hence they are both eventual upper bounds. Since u is an eventual upper bound to x sub n, and v is an eventual upper bound to y sub n, this means that eventually we have u times v is bigger than the product sequence. In steps 3 and 4, this is made rigorous by using the definition of being an eventual upper bound, which is given in terms of finding a term n beyond which something holds. So what is there left to do? Our goal was to start with a number that is bigger than the product of the limsups and conclude that this number is an eventual upper bound of the product sequence. What we have accomplished so far is shown that if a number can be written as a product of u and v, each of which is greater than a corresponding limsup, then what we want holds. So we need to do some arithmetic to show that any number that is bigger than the product of the lim_sups can be written as a product of two numbers that are individually greater than one of the lim_sups. Before we move on, you may ask why in the theorem statement we require the two sequences to take positive values only. The most important use of it is on this slide, and it is not step 1. It is, in fact, step 4. We're using the fact that for positive numbers, multiplying two larger numbers leaves the product larger than that of two smaller numbers. If the numbers were allowed to be negative, then this inequality can switch directions. So let's first do the case that one of the two lim_sups is 0. Since it doesn't matter which one, we suppose lim_sup xn is 0, and therefore the product of the lim_sups is also 0. Now let z be any positive number, so it is bigger than the product of the lim_sups. If we take v to be any number bigger than lim_sup of yn, it must be positive. And so the number epsilon, which is z over v, is also positive. And so it is an eventual upper bound of xn. So we see that z can be written as a product of a number epsilon that is greater than lim_sup of xn, together with a number v that is greater than the lim_sup of yn. So from the prep work, we know that z is eventually greater than the product sequence. And we're done. Now let's do the case where both lim_sups are positive. Let's take z again, something bigger than the product. Remember, we wish to show that z can be written as u times v, where u is bigger than lim_sup of y and v is bigger than lim_sup of x. Now, since both of the lim_sup are positive, we can divide by lim_sup of x to say that z over lim_sup of x is greater than lim_sup of y. By the Archimedean property, we can find u in between. Incidentally, the worry about division by 0 is why we have to separate out the other case to do first. Notice that this u is greater than lim_sup of y, as we hoped, and also less than z over lim_sup of x. This is useful because if we set v to be z over u, then some arithmetic shows that v also has to be greater than lim_sup of x. So our job is done. We wrote z as a product of two numbers, one of which is greater than lim_sup of x, the other greater than lim_sup of y, and the rest follows from our prep work. So with the theorem proven, let's discuss a counterexample. This is not a counterexample to the theorem, but a counterexample to show that the theorem cannot be made more restrictive. The question is, can the inequality in the conclusion, which says that the lim_sup of the product is bounded by the products of the lim_sups, be strengthened, say, to an equality? The answer is no. And here's a simple example. That x sub n be the sequence minus 1 to the power n plus 2. That y sub n be the sequence minus 1 to the power n plus 1, then plus 2. Both sequences have positive terms, and they have the same lim_sup, which is 3. This value is achieved every other term for both sequences. But if we look at the sequence of their products, we see that when xn is 3, then yn is 1. And when yn is 3, then xn is 1. So the product sequence is in fact a constant sequence that equals 3 for all n. And so its lim_sup is equal to 3, which is certainly not equal to 9, the product of the lim_sups. So why is this? The reason is that when we take the product of the lim sups, we are taking in some sense the largest possible value of x and multiplying against the largest possible value of y. But in terms of the sequences, it is possible that the two sequences are out of phase, so to speak. So when one sequence is large, the other is small, and vice versa. When this happens, you can never get two of the large numbers multiplying against each other. So the lim sup of the product is smaller than the product of the lim sups. If you have studied some physics before, this is kind of like constructive versus destructive interference. When the two sequences interfere constructively, then the most we can get for the lim sup of the product is the product of lim sups. When the two sequences interfere destructively, the lim sup of the product can be much smaller. But how much smaller? The next theorem gives the answer. This theorem says that the lim sup of the product sequence is no less than the lim sup of one times the LIMINF of the other. Going back to the constructive versus destructive interference picture, the largest lim sup achievable with the product is when the two sequences are exactly in phase, so that the largest terms of one is multiplied against the largest terms of the other. Similarly, the smallest lim sup that is allowable with the product is when the two sequences are completely out of phase, when the largest terms of one is multiplied against the smallest terms of the other. In other words, this is the picture of lim sup of one multiplied against the LIMINF of the other. Notice that in the theorem statement, we chose xn and yn and take the lim sup of xn against the LIMINF of yn. The xn and yn are just labels. You can equally choose the lim sup of yn to multiply the LIMINF of xn. In fact, the lim sup of x times the LIMINF of y and the LIMINF of x times the lim sup of y may give different values. The larger of the two should give the more useful lower bound on the lim sup of the product sequence. Before we discuss the proof, notice that from the interference picture, you should expect similar statements also for the LIMINF of the product sequence, when the two factors are both sequences with positive terms. On the exercise sheet, you are asked to prove the LIMINF case yourself. Let's give a quick overview of the proof before we start the details. First, notice that if either lim sup x or LIMINF y is 0, then there is nothing to prove. Since the product sequence has only positive terms, we know that 0 is not an eventual upper bound. So our corollary from earlier tells us that the lim sup of the product sequence is non-negative. So we can assume both are positive. Because of our corollary, all we need to do is show that every number u that is less than the product of the lim sup with the LIMINF is not an eventual upper bound. Because this will tell us that the eventual upper bound is at least u. Since u is arbitrary, this tells us that the lim sup of the product sequence is an upper bound for the upper interval from negative infinity up to the product of lim x against a LIMINF of y. And so the lim sup of the product, being an upper bound, is no less than the lim sup of the interval, and this is what we want to show. So again, our goal is to show that every u less than the product is not an eventual upper bound. When a number is less than the product of lim sup of x against LIMINF of y, both of which being positive numbers, this number z has to be either positive or not. We first treat the case when z is non-positive. In this case, since the product sequence has all positive terms, we know that z cannot be an eventual upper bound, so we're done. So we're down to the case where z is positive. We proceed similarly to the earlier scenario. Since z is positive and both limsup of x and liminf of y are positive, we can divide z by liminf y and get a number that is less than limsup x. We can choose u to be between z over liminf y and limsup of x. Our choice makes u not an eventual upper bound for x sub n. Let v be z over u, then our choice of u forces v to be less than liminf of y. This means that v is an eventual lower bound of y sub n. The latter shows that there is some n such that beyond n the sequence y is greater than v. The fact that u is not an eventual upper bound of x means that for every m somewhere beyond both m and n there is an index k such that x sub k is greater than u. This means that for every m, there is an index k greater than m, such that x sub k times y sub k is greater than z. This means that z is not an eventual upper bound. And this proves the theorem. The two theorems we prove in this lecture are intuitively obvious once you get used to the dynamical picture of sequences and think in terms of constructive and destructive interferences. However, as in many times with this analysis course, the devil is in the details. You may wish to open up the slides in your browser and spend some time thinking through the two proofs to make sure you understand the logic behind all the steps. Okay, that's it for this lecture. See you next time.